Welcome at this last lecture of this MOOC. In this lecture I will look at hierarchical organization of components such that we can do intermediate reductions and deal with larger systems, and I also want to look at the explicit specification of external state spaces because that makes the intermediate state spaces even smaller. We saw this small system in the last lecture, and this is a typical software architecture pattern where you have a manager process controlling a number of workers. If we have a big system, then these systems often have this particular structure. So then we have the worker controlling sub-workers, and these sub-workers controlling sub-devices of devices, and they may even in turn control sub-devices. If this is our structure, then we can actually use what's called compositional state space generation and intermediate reduction. So the idea is the following: we take a subpart, and if we have this particular subpart, so let's isolate it, then we can actually generate the state space of this subpart by first hiding the communication, then generating the state space. The state space may still be substantial, then reducing it, for instance, modulo branching by simulation, hopefully getting a small transition system. And if we have this small transition system, we can replace the original behavior by this reduced behavior. And in this way we can work our way and replace all subsystems by this small behavior, and we can actually recursively do this upwards, so take this system and generate a small behavior of this system. Because we reduce all the behaviors before connecting them, the state space in this way remains much smaller than when we would generate the state space of the whole system. So this is a typical way to deal with very complex systems and generate a state space for the whole system. And the guideline is, in this case, that if we make our systems hierarchical, this works quite well. So typically what we do is we iteratively hide communication of a subpart, we generate the transition system of that subpart, we reduce the behavior, and ultimately we get the behavior of the whole state space, and if it is sufficiently small, we can inspect it or we can verify model formulas on it. There are a few disadvantages. The first one is that it only works for hierarchical systems. If systems have another structure, then this approach can even fire back, in the sense that intermediate state spaces are much larger than the ultimate state space. So if one wants to apply this, one should avoid such more complex communication structures. The other observation is that the behavior of systems, if you combine a number of subparts, often is more complex than one would expect. And that is due to the fact that if you do not think about the desired external behavior, you get more or less the external behavior that's in the subcomponents, and that's more or less accidental. So what one should do is that one should first design the external behavior and then adapt the subcomponents such that this external behavior is actually realized. And that's an important guideline, and if you apply it in combination with hierarchical systems, allows you to completely model and verify big systems. So the idea is you design the behavior of a subsystem, you then consider the subcomponents that are part of the whole system, and you adapt and tweak the subcomponent such that the desired and nice external behavior is actually obtained. And if you do this at all the layers, you obtain a system that is not only having nice behavior, but that's generally also much easier to understand for other people, and with that much easier to maintain, and this is one of the biggest issues with software these days. And it's also the case that the state space remains much smaller than if you just take a number of subcomponents and let the external behavior come into being. So let's just illustrate this with a small example. I look at the device monitor controller. Actually, it's inspired by Tannenbaum's third sliding window protocol. Tannenbaum's third sliding window protocol has an appalling complex external behavior, but it's a little bit too complex to explain here, so I simplified it somewhat with a device monitor controller. So, but it illustrates exactly the same phenomenon. So what we have is a device monitor, and that looks at devices and observes that they are correct or not and reports about it. We have a controller, and the controller has as tasks that it should report about the broken devices in sequence. So it first reports about 1, then about 2, and then about 3, etc. The controller has a buffer. The size of the buffer is M, because there are M devices, and it simply can record for every device whether it's broken or not. And the device monitor simply indicates that a particular device is broken whenever it detects it to the controller. So it could be that it first reports that 3 is broken, then 1 is broken, 5 is broken, 2 is broken. And it's now the task of the controller to report that back. So it will first report that 1 is broken, then 2, then 3. Of course, it will not report that 4 is broken, so it will skip that. And then reports that 5 is broken. And that does it with the simple out action. And this is a little bit simplified in the sense that it does not report which device is broken. It only reports that a device is broken, and it will report it in order. Well, the system is slightly more complex, so the user of this system that receives the out messages can stop the system, and it can again start the system. And when the system is stopped, there will not be out messages. That will only be delivered after the system is started again. So how do we specify this? We simply have the behavior of the controller. The controller has a buffer, which is just a function from natural numbers to booleans, indicating that a device is broken by true and that a device is correct by storing false. It has this boolean b, and b indicates that the system is working and can deliver out messages, then b is true, or it has been stopped, and in that case b is false, and then it is not allowed to deliver messages. And there is this index I, that's the index of the next device of which it must be reported that it is out of order. So what is the behavior? Of course, the device monitor can always report that a particular device is broken, so it can do this broken N action, indicating that device N is broken, and then the controller sets the position N in the buffer at true. It can be that the controller wants to report. So this can be done if B is true, because then it is allowed to report, and the buffer at position I should be true, because that indicates that device I is broken, and then it will do this out action. It will set the buffer at that position to false to indicate that it has been reported, and it will increase its index. If the buffer at the device at position I is not broken, so the buffer at position I is false, then it will simply increase its index and it will not report anything. It will do this internal tau action. And then we still have the start and stop actions. So if there's nothing to report anymore and the controller is allowed to report, it can be stopped. and we will set the variable b to false, indicating that it can now not report anymore. And if it's not allowed to report, it can be restarted, and then this Boolean b is set to true. So this is the behavior of this system. I think it's pretty straightforward. And the question is, how does the external behavior look of the combination of these systems? So we hide the broken action. In line with our previous lectures, we take the buffer size to be small. Actually, we could have taken it to be 1, but in this case we take it to be 2. And we get this state space, and this may surprise you somewhat. So if you look at the details of the state space, you will find that this is indeed correct, and this is reduced modulo branching by simulation, but this is not quite what one would expect. And if you look at increasing buffer sizes, we see the following, namely in the second column we see the sizes of the state spaces before reduction, and we see that these sizes are growing exponentially, and that is what we expect. This is quite normal, but we see that the external behavior, so the behavior after reduction modulo branching by simulation, has also an exponential growth. So if the buffer size is set to m, the total state space is already 2000 states big for the reduced behavior. And that looks quite weird. So we can ask ourselves, what is actually the behavior that we desire now that we see that this behavior that came into being is somewhat complex? And if we start thinking about this, then this might be the behavior that we desire. Namely, if the system is off, it will not report. If the system is on, it will report that certain devices are out of order. And that is what we expect to see. And now the question is, if we look at this original specification, why isn't it the case that we get this nice and expected behavior? And it turns out that the problem is here. We can only stop the system if we have nothing to report anymore. So what we could do is that we say we can always stop the system by hiding this part of the condition. And what we see is that in that case, the behavior of the whole system becomes all of a sudden this desired behavior. It's just this particular detail in a condition that causes this enormous and horrendous external behavior. And what we also see is that this is completely independent of this buffer size. The external behavior always reduces to 2. And what I think is that this shows that by consciously thinking about how the external behavior should look like, one can indeed make systems with much nicer external behavior than that's done these days by many people that are not aware of the existence of external behavior. Okay, let's look at an exercise. So here we have a small hierarchical system, and the system does the following. We have these processes P1 up till Pn at the bottom. They get triggers. All these triggers are the same. Whenever they get a trigger, they report that to the layer above. So P1, after getting a trigger, reports to W1 that it got a trigger, and W1 will then report it to M, and M does nothing else than simply reporting the trigger upwards. If we hide all intermediate communication, so only the triggers at the bottom and the triggers at the tops remain visible, then the question is, what is the size of the whole state space? That's the first number in the answers. The second question is, what is the size of the system modulo branching by simulation? That's the third number in the answers. That's the second number in the answers. And the third question is, what is the largest intermediate state space if we generate the state spaces compositionally and reduce them modulo branching by simulation. And that is the third value in the answers. So what did we see? The first observation was that if we have large systems, then it's a good idea to design them in a hierarchical way, because then you can generate the whole state space by doing compositional state space generation and intermediate reductions, modulo branching by simulation. This works much better than just generating the state space of the whole thing as a whole in general, but you can do even better if you design explicitly the expected behavior of the expected external behavior of all intermediate components, and you adapt the individual subcomponents such that they realize exactly this expected behavior. And if you do so, I think you are among the best if it comes to the design of complex behavior of these kind of systems. This brings us to the end of this fourth MOOC. And I hope that you have learned how to specify the requirements for realistic systems. I hope you have a feeling that you can specify realistic systems, and in particular do this in such a way that you can avoid the state space explosion problem. And this means that you are now ready to bring your knowledge into practice. And that is what we will do in the next MOOC. There I will ask you to design a controller for a realistic system. And what you have to do is first write down the requirements, then make a model of the system, prove that your model satisfies the requirements, and this means that you have a design ready for an implementer to build a trustworthy system. Hope to see you in the next MOOC.